Alrighty, let's start actually laying out our board. The very first thing we want to do, similar to in our schematic, is filling in this little information block in the bottom right hand corner so that we know if we are going back and editing this design later, when the last time we edited it was, what the purpose of this design is for, so on and so forth. Or if we pass this design on to someone else, they can also pull that information and see who the original author was, for instance. So again, we're going to double click on any of the fields in this block to open the page settings menu. I'm going to import today's date. I'm going to call this version 1.0. Give it a title, which is USB flashlight. Company, Florida Polytechnic University. Comment, author, Kevin Ractu. I'm going to leave the page size the same and the orientation the same as the default values, and I'm going to click on OK, and we'll proceed with actually creating our board layout. Now, very first thing we want to do is let's import all of the details that we filled in on our schematic when we were annotating into our actual layout, so we can see what those footprints will actually look like next to each other. For that, we can click on this button up here that says Update PCB from Schematic. You can also press your F8 key on your keyboard. If we did all of our annotations correctly in the schematic section of this video series, then we should see no errors here. If it says that there's a footprint missing, then you're going to have to go back and annotate that component and make sure you select a footprint for it. We're going to leave the other values at their defaults and click on Update PCB. Now we can click Close, and you'll see that as we move our cursor around, the footprints for each one of our components are also present. So we can put that wherever on our schematic we want. I'm going to put them near the top left corner. Now, we can see that a bunch of different things appear on this layout in various different colors. Remember I said earlier that this purple one, the courtyard, is basically an outline that's used to prevent components from intersecting with each other. The fabrication layers, the f.fab or b.fab, are just used for basically describing to the designer of the board or the manufacturer what each component does, or maybe drawing outlines for things to use as reference. It's not actually printed on the board and not actually used for any cutting of holes or etching of copper or so on and so forth. So we can go ahead and hide those layers so we're not as cluttered. I'm going to click on the little eyeball icon right next to the fab layer right here, and you'll see that those vanish. This is much easier to make sense of. The designators that we gave it earlier, the reference values like J1, show up right above the components. We can click on these and move them around wherever we like. And this is really the very first instrumental part of your actual layout of your printed circuit board, which is placing all of the components in an orientation that makes sense. So, for instance, we have our USB connector here, and we can see that based on this courtyard, the USB connector is projecting out to the right. I want to flip this around so that it's going to the left, just because it's easier for me to visualize like that. So while clicking and dragging, I can press on the R button to rotate it by 45 degrees at a time. And I'm going to place that somewhere here. Now, this part of the connector is actually past the PCB edge, as is labeled on here. I think that's on the drawings layer. That part, we don't want anything to be to the left of that, because this is where the actual USB connector is. That's not where our board is. Our board should cut off before that, or to the right of that. So let's move the reference designator so it's somewhere over that's actually on the board. So I'll put it somewhere here for now. We'll move it around a little bit more later on. And now we want to, let's place the resistor you can see these little blue lines coming out of each one of the copper pads. These are the nets of each pad, or electrical networks, right? You'll see that because we connected on our schematic, we connected the 2 pins on the USB connector to ground, and then we used the same global label for this end of the resistor, that there's a net line, a blue line, connecting the ground pad of the resistor to the shield pads of the USB connector and pin 4 for ground, which is exactly what we see over in our schematic here. Now, basically, we want to place our components in a way that those nets, those blue lines, are very close to each other. They're very short. So I see that ground of the resistor goes to ground of the USB connector. So I'm going to rotate the resistor and place it right next to it, like that. And place the resistor right next to the USB connector. So this blue line showing that the 2 grounds need to be connected together are very short. And then we can take our LED and see how that needs to be placed. So we can see that the anode, pin number 2 over here, needs to be close to pin 1 of the USB connector, which, if you remember correctly from our schematic, is V bus, or the voltage bus, the input power from the connector. So I want to rotate this as well. Let's spin it around this way. And if we put it right here, our lines between each component, the blue net lines, are extremely short. This is probably the optimal layout for our entire board. You'll see that we have some overlapping yellow text here. Yellow lines on our layout indicate that this is on the silk screen. The silk screen is what is printed on the board. It's not copper, it's not conductive, but it's just ink that's printed on the board to help label things or to show where certain components are or what they do. If you put a logo on your board, it would also be on the silk screen. So we can move those around wherever we like, as long as it makes intuitive sense. With these reference designators, it's a good idea to leave them visible and right next to the component that they correspond to, just so that we know what each item on the bill of materials corresponds to on the actual physical layout. So I'm going to do that and make sure that they're all in the same orientation, like so. And you'll notice that I'm being careful to not let any of the purple lines overlap. If I do, say if I drag the LED over the purple line of the LED over the purple lines of the USB connector, you'll see that they turn red. That's KiCad telling me that the courtyards are overlapping, and we can't do that. That would make, imagine if we tried mounting an LED on top of the USB connector. It just wouldn't work. So I'm going to give them a little space between each other and put them in an orientation that makes sense. And this should be good. Now we have to draw an actual outline for our board. And remember, for that, I said that we need to use the edge cuts layer. We're just going to keep this a very simple rectangular layout, a little square maybe for our flashlight module. So to select the edge cuts layer to be the one that I want to draw on, I'm going to click on the little empty space over by that gray colored box next to edge cuts right here, and you'll see a little black arrow shows up next to it indicating that it's selected. Now I want to draw a square to go from where this PCB edge is labeled to encompass all of these other components. So for that, I can click on this little Draw Rectangles button over here. And then starting from the top left corner, from where I want that square to start, I will click and I will drag. Oh, my bad. Depending on how your presets are, your preferences are in KiCad, you might have to click or drag, or you might just have to click once and let go. And then once you've released, it will continue drawing the square until you click again, or the rectangle, I should say. So I'm going to draw that rectangle so that it encompasses all of the components, and then click again to finish placing it. If you wanted this square to be a very precise set of dimensions, say I already had a 3D printed enclosure for it, and I wanted it to fit nicely within that, I could double click on that outline and then select on the by corner and size dimensions tab up here, and then say that I want this to be a 14 by 15 millimeter square or rectangle. And the dimensions of that square or dimensions of that rectangle will adjust automatically. So now I can just line this up with where I need it to be. Remember that PCB edge text and that line that is on that footprint, those are on the user drawings layer by default. So they don't actually show up, they're not printed on the board. So I can deselect that if I don't want to see it anymore. And then this should be a fairly accurate representation of what the board actually looks like. And if we selected all of our components correctly, we can now go over to View and then 3D Viewer, and KiCad should show us what our board looks like. Now, it's not rendering the USB connector. That might mean that the model is not included for it by default, but yeah, typically with models that KiCad has built into its libraries or has included in its preloaded libraries, they already have 3D models to represent all the components, like this LED here or that resistor right there. I'm a little surprised that that USB connector isn't included, but you would have a USB connector sticking out on this left side here. We can see that the copper pads are in exactly the right place, and the cutouts to actually mount the connector are in the right place. So this 3D viewer is extremely useful for visualizing what our board will look like. Now, suppose you didn't want a perfect little rectangle like this and you wanted to round the corners. Well, you can do that too, but it does take a little bit more effort. You'd have to draw arcs. Say an arc like this. I'm going to give it a radius of 1.2 millimeters. There are a bunch of different ways to do this, some faster than others. And then I would line them up on top of that square. I'll copy and paste that arc, rotate it, and fit it into each one of the corners here. Like so. Just like that. And now I'd have to delete the original square because there's some overlap here, and instead draw lines between those arcs. There are a bunch of different ways to make outlines like this, some more convenient than others, but this is the one that I've used the most often, so I tend to be able to zip through it a little bit. Like so. And right there. And now, if we go back to our 3D viewer, you'll see that we have rounded corners. A tidy little 1.5 centimeter circuit board that with a USB connector on one side and an LED that would come on if we plugged it in on the other side. Now, we are not done. Definitely not done yet. You'll notice that our blue net lines are still there. These are not actual connections between those copper pads. These are just telling us where those connections need to be. So now we need to actually draw the traces connecting each pad to each other. And for this, let's first select what size of trace we want to use. Remember when we filled in that menu previously showing all of the different trace or track widths that we'd be willing to use in the future, we only included the one row for 0.2 millimeters. So that's why only one row shows up here. So I can select that one, And I can also select our via size, which is 0.7 total diameter, and then 0.3 millimeters for the drill hole, right there. And now we can actually start drawing traces. A few different ways to do this. We can click on this button right here that says Route Single Track, and then click on the pads we want to draw connections between, like that. Or you can just press the X button while hovering over a pad that you want to start a track on and continue drawing that line. So now you'll see that we have a track going from the positive terminal on our USB connector to the anode of our LED. We have a track going from the cathode of our LED to one terminal of the resistor. And now we can complete the circuit by putting a connection from the ground point of our resistor to the ground terminal of the USB connector. Now you'll notice that the two shielding tabs on the USB connector also need to be connected to ground. I could do this. I could add tracks from ground to the singular ground pad like this, but that's depending on the type of board you're building. There can be different reasons to do that or to not do that. What's more common practice, especially with two-layer boards like this with a large ground, is you can use a copper pour. You can use an entire filled area that connects to the ground instead of just a single thin line, and that ensures a more reliable connection to ground. It also prevents, or it absorbs stray electromagnetic radiation to keep interference from hindering the performance of your board. With a very simple light design like this, it wouldn't really make any difference, but I want to use this opportunity to show you how to draw those copper pours. For this, we click on the Draw Filled Zones button over here. Well, actually, before we do that, one thing that I need to show you. You'll notice that my grid that whenever I click that different things snap to, my grid is, here, let me switch back to my front copper layer. My grid is very, very narrow. I have a lot of precision, a lot of control over where things are placed. But what if I wanted things to snap to a line to maybe one particular grid item? I can adjust the grid size up here, right in this drop-down menu. Currently it's on the very smallest value. I could bump that up to, say, 1 millimeter. And now if I try to click and drag, you'll notice that my components are snapping to 1 millimeter increments. I don't really need this right now, but it'll actually be really useful for drawing our copper zones. So I'm going to undo to put my LED back where it was with Control Z. And now leaving my, or actually I'm going to change the grid to maybe 0.2 millimeters to give me a little bit more control over the snap of that grid. And now I will start drawing a copper zone. Make sure that the specific copper layer that you want to draw your zone on is selected. So for me, it'll be the front copper layer. And we will place one corner of the square roughly around the corner of the board. Once you click the first time, it'll ask you what electrical network you want this copper zone to be connected to. I'm going to select ground. We want all of our grounds to be connected together. And now there are lots of different options in this menu. If you have a bunch of different copper pours laying on top of each other and you don't want them to intersect, you have to give them different priority levels. You can give them clearances, how far you want them from the edge of the board, or what the minimum width is before it just doesn't even fill in a section. But then also one that you want to pay attention to is this pad connections menu. There's a thermal reliefs option, there's a solid option, there's a relief strip plated through holes, PTH option, and there's a none option. Let's leave it on thermal reliefs to show you what this looks like first, and then we'll come back and switch it afterwards so you can get an idea of what that looks like. So I'm going to click OK, and you'll see that it's still drawing a line right now. That's because it's waiting for me to finish drawing the copper zone that I want to be filled in. You'll see that mine is currently snapping to 45-degree angles. That is an option that can be toggled over here with this constrain to HV45 option. You can also toggle it with the shift space shortcut. If I turn it off, you'll see that I can place this zone wherever I like, but to keep it tidy in a perfect rectangle, I will leave it on to that snap. And I will click at each corner of my rectangle and draw that copper zone. And then finally, I'll come back around to the first point, click there to complete it. And you'll notice now that we have this sort of hatched rectangle. And if I press B, it'll fill in that rectangle with copper. So basically what this does is everything that was assigned to the net, remember whenever we drew this, or whenever we started drawing this copper zone, it asked us what net we want the zone to be connected to, and we selected ground, right? So now everything that is connected to ground is connected to one big copper pour. This makes it really easy for things like ground that are usually abundant. They're all over the place on a board. So instead of having to draw individual traces like this little one right here, we can use the copper pour to automatically connect them together. Now you'll notice that the ground copper pour is connecting to all of my grounds with these thin little spokes. Those are thermal reliefs. Those are tiny little spindles that allow plenty of electricity to flow through, but they don't allow that much heat to flow through. That's intentional because sometimes, say if I was hand soldering this component to the board, if I was trying to solder this ground pin with my soldering iron touching to that pin there, it might not heat up well enough to melt solder onto it, just because if there's so much copper connected to it, it'll dissipate the heat so fast that the solder won't melt. That's why we would use thermal reliefs like this, so that heat only dissipates at a much slower rate. But if I don't really care about that, if I'm not going to be hand soldering this, and I want a better ground connection, I can go back by double clicking on that copper zone and change that thermal reliefs to solid. Click OK, and then press the B key again to refill all of my zones, and you'll see that it completely filled in all of the grounds. Now all of my ground pads are connected directly to the entire top copper layer, which is used exclusively for a ground. And all of the other copper pads, say the positive terminal down here, it's not being connected to the ground pour, because they're not on the same net. That's why it's super important that you select the right net whenever you're defining a copper zone. So now this is our functional board. This would work. This is actually something that we could have manufactured, plug this into a USB port, and our LED light would come on. Just to show you what this looks like after routing all of the traces, we can go back to our 3D viewer, and you'll actually see the outlines of your copper traces. You can play with all of the different color presets in here to make things more or less visible. For instance, if I wanted this to be a darker green, I could switch this to green. We'll darken it a bit. Do the same thing with the other side. No, I think it already applied to both sides. But yeah, so we can tinker with the appearance as much as we like, but note that what we're seeing in this render inside of the 3D viewer isn't exactly how it will look after you've had it manufactured. Whenever you're actually ordering the boards, that's when you'll have to tell the manufacturer what color you like. That's why some of these are, black, and then I have others that are green or yellow or red, so on and so forth. Green is the most common color, and it's often the cheapest as well, because that solder mask they use to make that green color is extremely abundant. So that is basically how we can design a very simple printed circuit board. But I do want to show you a couple of further tweaks, or a couple of tricks that we can use for more complex designs. I'm going to press Control B to unfill that copper zone, at least for now. What if we wanted, I'm going to delete the trace connecting, let's delete the trace connecting the V bus pad 1 on the USB connector to the anode of the LED. To do that, I can click on one segment of that trace and then press the U button on my keyboard to select the entire trace, and then just press delete to get rid of it. What I want to show you is how we can make use of that other side of the board, because remember, this is a front and back 2-layer copper board. What if I wanted to use, what if I switch over to the B layer here, the back layer? You'll see it turns blue to show that these are back connections. What if I want to connect this terminal on the back to the V bus pin on the USB connector on the front? I could start the trace on the back like this, but then I need a via to tunnel through to the other side. While I'm drawing the track, I can press the V button on my keyboard and you'll see that dot appear. That is a via. And if I click, it'll place the via and automatically flip me over to the top side of the board, connecting using that via as a tunnel through the 2 layers of the board. And now, just like that, my front and back layers are connected. That trace goes on both the back and the front of the board. On this design, this is so simple that there's really no reason to do that, but sometimes, say you have 2 different traces that you don't want intersecting. Sometimes you'll need to poke through one side of the board and come back through the other. Let me give you an example of that. Let's say I wanted to, here, let me flip back over the top layer. Let's say I wanted to go past, I wanted to route my anode trace, the positive trace for the LED, past this negative trace. KiCad will not let me cross the 2 because it knows that they're on 2 separate nets, 2 separate electrical networks. So in order for me to get past that, I either need to go around it like this, or I can use a via, punch through the board, cross it on the back side, and then punch back through, and then complete my circuit. That is one of the primary uses for vias, for just using the back layer to get around obstructions on the front layer. Again, there's absolutely no reason to do that on a board this simple, so I'm going to go back to our very basic layout like this. Press B again to fill in all of our zones, and there you have it. There is our board. Now, the next thing I want to talk about is the design rule checker, the DRC, that helps us catch a lot of errors that we might have with our board before we send it off to get ordered. And that's what we'll be talking about in the next video.